Hello, I'm Arabo, and we are Team 205, Industrial Automation Machine. The goal of our project was to make any sort of automation machine that could sort and automize a certain industrial process, and for our project, we made an eddy current separator. The goal of our project is to separate non-ferrous metals, and plastics. So this machine is mainly used in the recycling industry to separate out any different metals and sort things properly. The main culprit is aluminum cans. So our project was split into three phases. The first phase covers the magnetic separation, which we separate out the ferrous metals like iron, and then non-ferrous metals like aluminum or copper. This consists of two conveyor belts with magnetic rollers that spin at different speeds that can separate out these different types of metals. The first one is just a normal magnet holding the iron onto it. The second belt consists of a very fast spinning magnet that can generate eddy currents and fling metals off of the conveyor belt. The second and third phase deal with separating the plastics. The second phase separates them first by size, and then the last phase separates them out by color. So this is our agenda. For phase 1, Walter will cover the conveyor belts, Jaime the structure, and I'll explain all of the electrical and magnetic parts. For phase 2, Jesus will cover the design, Mitchell will cover all the manufacturing process, and Alex will cover all of the testing and results of their size sorting. Then for phase 3, Xochitl will cover the design and the sensors, Ryan will cover the motors, and Hermela will cover the final part of that phase.
This portion of the automated machine was designed as a scaled prototype, replicating key separation methods to isolate ferrous and non-ferrous metals, as well as plastics that are utilized in industrial recycling. Its operation is predicated upon fundamental material properties, specifically magnetic and electromagnetic sensitivity. It works in conjunction with motorized actuation. Eddy currents are a phenomenon that occur when a conductor is exposed to a changing magnetic field. Eddy currents create flows that generate their own magnetic field, which oppose the original one. The result is a repulsive effect that pushes conductive material away, in this case, the remaining metals. This was done by designing a drum with alternating magnetic poles, rotating at a fast pace, creating the repelling force necessary. Increasing rotation speed increases the force. Conveyor belt 1 functioned as a straightforward mechanism. A drum positioned near the material drop-off zone was fitted with magnets. As materials passed over this section, only magnetically responsive metals adhered to the rotating wheel, traveling along its underside until they eventually released as the belt completed its cycle. This process transferred the remaining materials to conveyor belt number 2. The design of the second conveyor belt incorporated greater mechanical complexities. In this initial robust configuration, a horizontally oriented support beam was employed to maintain appropriate belt tension, ensuring sufficient friction for effective rotational motion. Positioned near the head pulley, a magnetic drum was mounted within a stabilizing wheel assembly, held upright and in close proximity to the belt surface to facilitate ferrous metal separation. Operationally, the system required two distinct motors, one calibrated for slow, consistent movements of conveyed materials, and the other configured to drive the magnetic drum at a high rotational speed necessary for magnetic interaction. To accommodate a rapidly spinning magnet near the drop of the zone, the wheels were enlarged. This configuration enabled the generation of an eddy current capable of repelling non-ferrous metals away from the remaining material streams. Through this effect, this portion of the machine would have successfully separated plastics from both ferrous and non-ferrous metals. In designing this conveyor belt, one of the biggest challenges we faced was the speed of the magnetic drum. Because it rotates at such a high rate, the materials used initially for the structure had to withstand significant rotational stress. Our initial design revealed several weak points that were susceptible to breakage under these conditions. To ensure reliable operation, We needed to move towards more rigid and durable construction, capable of handling the forces generated by fast rotation. In addition, the conveyor belt did not allow for adjustability for magnetic roller. It was later discovered a more reasonable angle for the magnetic drum would be arranged between 60 to 80 degrees. Original design did not allow for adjustability. In the final stage of design, it was refined to address both structural strength and sustainability of the magnetic drum. To achieve this, quarter-inch thick aluminum plates were incorporated, replacing the polyester body. This was unnecessary, ensuring the system possessed the rigidity required to withstand operational stresses, while allowing for the precise alighting of the magnetic drum.
Phase 1, the conveyor belt structure. The conveyor belt structure was originally designed to be 3 feet in length by 2 feet in width and 2 feet in height. These dimensions were chosen to provide a compact frame that offers sufficient structural strength to resist any bending under operational loads. The compact footprint allows for easier integration into confined or modular workspaces without surrendering functionality. Constructing the frame from either steel or aluminum was the initial idea, since it provides significant advantages such as offering load capacity and rigidity. The specs ensure the frame is strong, stable, and compatible with function demands of the conveyor system. Nevertheless, the team came together and agreed that the tubes were too heavy overall. This is due to the reason that each tube felt too heavy and we needed something lighter for compatibility. As a result, the steel bars were put aside and we decided to aim for wood as the new ideal material. This plan allowed for a more safer option for the eddy current and easy installation for phases 2 and 3. The frame was then completed and built out of 2x4s. When designing the structure for a conveyor belt, the first idea in mind was to implement the belt width based on the sizing of the structure. Along with the belt width, we focused on the different components such as rollers, supports, and rods. This is important since there is a limited space for handling the movement of materials. For the conveyor with the eddy current roller, the first design approach was to create a roller that is 3 inches wide in diameter to cover the magnetic roller. This allows for shielding of the roller to prevent the belt from intertwining with the conveyor. The CAD was created and ready for construction until we ran into a few problems. The machining of the rod where the eddy current magnet would be sitting was difficult due to the precise cutting that left the ends of the rod uneven. For that reason, we spent too much time, and the design idea was then decided to go for a different approach. We grabbed the pillow blocks, square flank bearing rods, and 3D printed rods that would help in case the aluminum rods were not sufficient. The aluminum rods were working great when rotating slowly. We then attached the stepper motor to a rod, though we were stuck on how to secure it. By creating a 3D printed rod with a keyhole, this allowed us to fit the motor shaft onto the rod without further issues. The next phase was grabbing the dimensions of the belt. We decided to go for 2 feet in length, and nevertheless we ended up having the first conveyor belt to be 1 foot and the second one 1.5 feet. We chose these proportions to give advantage for the stepper motor. When constructing both belts, we bumped into some difficulties of transferring power to the rods that are operating all together. The initial plan was to grab a chain and sprocket combination and attach it to 2 ends of a pair of rods. This helps drive the 2 belts by distributing power from 2 different separate components. After the attempt of attaching the chain and sprocket, we ran into difficulties such as the proper tension and adjustment of the 2 belts. We attempted a different approach and headed towards a serpentine belt and pulley system. The single serpentine belt wraps around both pulleys that drive the conveyor and rods. The power is distributed and delivered to both simultaneously. In addition, this method is lighter, which helped us save space compared to the chain and sprocket. After attempting these ideas, we began to test the motor that drives the eddy current magnet. The first test was a fail. The magnets flew off from the position, causing them to break into pieces. We then added more detail to the magnetic holders, such as screws, to help hold down the magnets more precisely. In addition, we created a hole on the side of the roller to fit the rod the size of the pillow block bearings in order to give it extra support. After the second approach of testing, the magnets commenced another breakout. They flew out of their place even after the improved design. This result is due to the motor providing too much power, causing the roller to spin aggressively and launch everything away from its position. Several attempts have been made, including trying to reduce the motor speed, but it keeps generating way too much power. The structure made out of the 2x4s also shook with too much vibrations.
For magnetic separation, the design of a magnetic roller is critical. So for the first conveyor belt, where we're just separating out ferrous metals, it is not too important. We just need a magnet to latch on any iron and hold it until it goes under the belt, separate from the rest of the process. But for eddy current separation, this becomes a lot more complicated, and the design is pretty critical to achieving eddy current separation. The whole idea of eddy current separation is to have alternating magnetic fields that generate eddy currents in non-ferrous metals on the line. These eddy currents generate their own magnetic field, resulting in a force that'll fling them off the line, separate from whatever else is on the belt. So for our roller, we picked the 4-pole design, and we want to spin it faster than our 3000 RPM. This is mainly because for a very common industrial application like aluminum can sorting, typical design is around 6 poles spun at 3000 RPM. So for us, who we really just want to achieve some form of separation, we opted for a 4-pole design, mainly because its size is less and its cost is less. There are less magnets. But to offset that, we need to spin it a bit faster, which goes into our motor selection next. For motor selection, so the main important parts are to drive the belts and also to drive the roller for the eddy current, magnetic roller. For the conveyor belts, it's rather simple. We just used a simple stepper motor and a driver to run the belt. These were already in the lab. It was free, and they got the job done. For the eddy current separator, it's a bit more critical. We need a pretty high RPM motor. We decided on a DC voter. So we found one already in the lab that could meet the desired RPM we needed. It was Amflow E15024. It has an nominal speed of 5600 RPM, so it's pretty high. And we also chose the BTS 7960 motor driver, so we could PWM control the speed of this motor. And to power these guys, we just got a pretty simple AC to DC converter that could output 24 volts and 20 amps. 20 amps is mainly just because the DC motor has an inrush current of around 20 amps, so we need to supply it so they can start. During this problem, we ran into some issues when testing our magnetic roller and some of our electrical parts. Firstly, we figured out that our 3 DC motor drivers were all defective. So unfortunately, they all outputted this strange waveform, as you can see on the slide. Now, this waveform showed up whether just power was applied or any control signal was applied, and also regardless of any input voltage changes. So it was very odd, and all 3 of them exhibited this behavior. We double-checked the documentation, made sure our microcontroller was outputting all the right signals, and this weird behavior still showed up across all 3 of them. Next, for the magnetic roller, the structural stability of all the magnets in the roller itself was pretty difficult, especially spinning at such high RPMs. Because we couldn't really speed control the DC motor due to the previous problem with the motor drivers, we had to run it at nominal speed, which is really fast. The problem is that regardless of what we used to try and secure the magnets onto the roller, they would fly off and hit into each other and break. So these are some of the setbacks we encountered during this project and in our testing.
In today's rapid industrial landscape, efficient material separation is more than just a challenge, it's a necessity. From recycling plants to manufacturing lines, companies are under growing pressure to reduce waste, recover resources, and build smarter systems. Our team wondered, how can we streamline metal separation and prepare for the growing use of plastics? In phase 1, the metals are put into a conveyor which will make its way into 2 different conveyors. In the first conveyor, the ferrous metal will be separated, and then afterwards, in the second conveyor belt, the non-ferrous metals will be separated. This allows for the complete isolation of plastics, in which it will be then separated by shape and size. For design 1, it requires a box shell and a triangular shaped device that separate each shape by respective size. In design 2, it will require 2 rods to be placed together at a certain angle from each other for the shape to fall off at a certain point when rolling down the tubes, similar to a gumball machine, not needing a shell box.
For design 3, we came up with a slide track design. This is a ramp that will be paired up with a shell box and will narrow down the balls into a single lane. We will use the spacing of the holes and the speed at which they are traveling at. It will grow into tubes that have 3 different lanes and that is able to separate each ball accordingly to its proper size. Our design didn't use any sort of mechanical parts to separate the plastics. We use gravity to make the plastics free flow through the box shell, and the curve in which the box will be rolling through has different sizing so that balls can fall accordingly into their proper lane. We implemented additive manufacturing into our parts to help ease the design changes and use less material. 3D printing is an economical solution for industries that require parts to be rapidly prototyped, and it is cost efficient. Our automation system can be used for different industries such as the management and recycling industry, which can be used to sort mixed municipal solid waste. It could also separate aluminum, steel, copper, and plastics. And it would also reduce manual labor and contamination. This would also reduce operating costs, improve the processing rate, and it is compliant with our environmental regulations. Some examples would be like private recycling centers, zero waste processing plants, and public recycling facilities. This can also be used for the manufacturing industry, which can be used to recycle production scrap such as metal shavings, plastic runners, and mold waste, and reusing raw materials in closed-loop manufacturing systems. And some applications can be in automotive manufacturing, plastic injection molding facilities, and metal fabrication shops. Some of the benefits would be reducing the raw material costs. It would also support sustainability goal and would also decrease landfill disposal fees.
The idea behind design type 1 was from a game called To the Moon, where the goal of the game was to position the two sticks at a certain angle to land the moon, the spear in this case, at a certain spot to gain points, as shown here in the picture. This led to our very first design known as chopsticks. The chopstick design was the very first design our team had produced. The idea behind this was that we would position the sticks at a certain angle from each other and have the spears roll down on them. As the spears are rolling down on the sticks, the spears will fall through the open gap of the sticks at a certain point for each size going from small, medium, large in that respective order. From this design, we were able to derive a few more designs with similar concepts as shown here in the pictures. One thing to take note of was that from each design, we kept clear of using any electronic components such as DC motors or stepper motors, making this design purely reliant on gravity and mechanical forces. The idea behind our second design was that we wanted to dispense the spears in a tiny manner, similar to that of a coin toy dispenser, so that we could avoid an overload or a clog in the second phase. This led to our second design known as the box dispenser. In our second design, we went with a whole new approach, with the design consisting of a box catcher and a water wheel inside the box being spun by a small DC motor, as shown in the pictures here. The design was still meant to use the very first design discussed here at the end. The box and wheel were here just to serve as some sort of dispenser to dispense the oncoming spears in a timely manner before separation. However, some of the problems derived from this design is that there were now several parts to this design, and on top of that, the use of power was now in place since we need a DC motor to spin the wheel to dispense the spears in a timely manner. This ultimately led to our third design known as the slide track. On our third design, this consists of a ramp-like slide with a cone-like bottom at the end, with open slits at the edges corresponding to two of the corresponding respective sizes, small and medium, with the third size being the large one, which will fall right off the track at the end. This, however, was our most promising design yet, as this design still follows the concept of the very first design, and on top of that, it was only just one part. And this also made it clear that we were not using any electronic components as shown here in the picture. We had made a prototype of this design and tested it, which shows some promising results for this section for many scenarios. These are pictures that we have of our current prototype and a current video on how it will function. As shown in the video here, we tested this device out in different scenarios where we throw 3 of a kind of each size and throwing in random sizes, one after the other. As shown here, we could see that each size was correctly separated to their corresponding sizes from small, medium, and large. Below this device is some sort of divider to divide each size from not mixing with each other, so that we can have it ready and prep for phase 3. The color design, or color separation.
Next, we have phase 3, the color organizer design. The goal of phase 3 is to organize the spheres by its color after going through the size sorter. The steps for the color organizer design. First, the sorted size spheres will fall into their specific chute. 2, the spheres will roll down and are pushed over one at a time into the funnel. 3, the spheres will sit at the end of the funnel where the color sensor will detect the color of the sphere. And once the color is detected, a silver gate will open. And step 4 Once the color is detected, the sphere is then sorted by its specific shape and color. Next, we have the CAD design of our color organizer. This is the first design that we went with. We designed it at an angle so that the spheres could roll down with momentum. The spheres will stop at the end and will then go down the funnel. The light sensor is positioned at the bottom to detect the color of the sphere. Here we have the final design of the CAD color organizer. As you can see, it's still similar to the first design, but we did make a few adjustments to make it more smoother and concise. The design is the same aspect as the previous design, where the sorted size spheres are organized by its color. The size spheres fall into the specific roll or chute, and here at the bottom we have 3 servo motors at the end, which will allow one sphere to roll over at a time into the funnel. The funnel holds the light sensor at the end, which detects the color of the sphere. There's also one more servo motor at the end of the funnel, which acts as a gate or door, which opens and closes and allows the sphere to fall into the next phase of phase 3. A few adjustments we made was adding a ramp to the end of the roll for a smoother rollover of the spheres. We also changed the positioning of where the sensor sits, and then we also added another servo motor to open and close after the color of the sphere is detected. Here we have the prototype of the color organizer. In the first picture, we are testing with the 3 servo motors to see if the motors will allow the balls to roll over smoothly. The second picture, we are testing with the funnel and ramp. Here we want to see if the spheres are rolling over smoothly and going into the funnel how it's supposed to be. And in picture 3, we're testing with just the light sensor. We want to see if the light sensor is detecting the correct color of each sphere.
So as shown earlier in our final design, we have 3 servo motors that will be pushing the ball into a tunnel where the color would be red. And those 3 servo motors are the Tower Pro SG90. The reason we picked this motor is because we were all familiar with it and we had a few of these lying around. We didn't need to order any more parts, we just pick these up and start using them. It's a geared motor capable of rotating 90 or 180 degrees, which is perfect for what we need this for. We just need to be able to push the ball up into the funnel where the color will be red. Once the color is red, our last Tower Pro servo would act as our door opening mechanism. As for our next servo motor, we'll talk about that a bit later. First, we're going to move on to our color sensors. The sensor we chose for detecting color is the TCS34725 RGB color sensor shown on the right. It fits all our needs for just reading red, green, or blue colors. Once the color of the ball is red, we'll have both the size and the color of the ball, in which it would send the information to the Raspberry Pi, and from there it will direct our servo motor, the final servo motor, to move the balls into its corresponding bin. Once the size and the color has been determined, it will push the ball into our final servo motor, the MG995R, which is controlling and driving our pipe, sending it into the corresponding bin of the ball. We need the pipe to be able to turn a factor of 20 degrees. That way, in a 180-degree radius, it can fit into 9 different bins. Originally, we chose a NEMA 17-stepper motor, but we soon found out it was incompatible with the Raspberry Pi. We could make it work if we stepped it up, because it's a 5-volt, and the Raspberry Pi we had only supported 3-volt, which is what the MG995 servo motor was. Here's what our sorting apparatus would look like. We would have our pipe setup with a funnel connected attached to our MG995R servo motor, and it will turn 20 degrees, 40 degrees, 60 degrees, all the way to 180 degrees, so it would fit 9 different bins. A recap on how this would work is, once the balls are sorted by size, the tower probe will kick up one ball depending on what size it is, and from there we'll know which size it is because we have 3 different tower probes, and each one will correspond to one size. Once we have the size determined, it'll be thrown into a color sensor, which it will determine the color of the ball. From there we have both our parameters met, the size of the ball and the color of the ball, and then from there our final servo motor, the MG995, knows where to put the ball based on those parameters. So it would be dropped into this funnel and it would be rolled into the correct bin. And then the process repeats.
My name is Hermela, and I'm going to present phase 3, the last part of the project, which is color sorting. And I do have an introduction for it, design materials, and I'll talk about how it configured. Introduction, this part of the project is the color sorting of the spheres after it's sorted out by a size of large, medium, and small. And then it's going to sort out by the color, red, blue, and green spheres, and then they will be sorted out. Each of them would have 3 sizes, 3 colors, and it would have total 9 cups or beans. I'm gonna use a cups in here. 9 cups. It's also can be used beans as well. And to achieve this machine, the materials are used: servo motors, Raspberry Pi 4, sensor, and some wiring and boards as well. which the sensor will identify the color, and then with the help of the machine or design, it will drop into the 9 cups or bins, which 3 cups for each color and size as well. Um, this right here is a Raspberry Pi 4 with their GPIO pin out. It has all the components of with the voltage sources and grounds as well. And we do have a servo motor in here, which has 3 wires. Red connects to 5 volts, brown was ground, and orange was PWM. Pulse width is modulation. And then we do have this design, which I designed it. I'll have a base at the bottom, and then this shield or cover to hold it. And then I do have in the middle a slider that will attach to a motor in here, and then it will rotate around this cups to drop the spheres, 3 rays in here with different sizes, and then and here a blue and a green as well in here. So totally 9. And these are all connected all together and with the rest of the design parts as well. How the parts work. So the servo motor, we choose it because it's a part of a project, and it is a special type of electrical motor, and it changes electrical into mechanical energy to reprocess electromagnetism. We choose this motor in most 180-degree, and we couldn't be able to use a stepper motor because we couldn't be able to handle the voltage as well. So we chose the servo motor, and it moves 180-degree, which is it fits our the cups that we need 180-degree so that it can rotate. Yes, it's will attach to the slider or the tube to move 180-degree, and the configuration configured with Raspberry Pi and code. Each bins or cups in here used will be isolated by a certain degree as well, and it will rotate through all the 9 cups. And the Raspberry Pi is a powerful compact board of a computer, single computer designed for many applications. It's small, but basically it's a computer. It integrates with a computer or laptop, which operates system support like micro SD cards and or USB storage. It has a GPIO pins right here, as we can see it, to connect with the motor control, to control the movement. Yes, we did the code. And then we do have pins. We do have the motors in here. We do have 3 wires in here. One is the red, which is attached to 5 volts that are in here. And then you have a brown or that's connected to ground. And then we have orange PWM, this in here. Put it all together. So I will rotate it with the code that we have. And at the end, the goal is to design a sophisticated machine to sort the codes into the desired cups. In here we choose spheres, but it could be anything. We just tested for this project, just a sphere. And the materials and the 3D design are prepared, which is one setback or problems or difficulties that I have. It's the materials are prepared. We're thinking to make it with the wood or just a foam board. That is also one ideal way to do it. And then also I have prepared the 3D design as you can see in here. Um, but it's not physically built. That's one difficulty. Throughout the process, I had an issue with designing the motor, which is the servo motor with 3D design, SolidWorks or Onshape. That's another thing for electrical engineering major to be able to learn on Onshape or SolidWorks softwares, which is another setback. It's difficult, yet we're learning. That's one important point of this project, being able to expose to different um, ideas and then materials and softwares. Uh, so that's one setback and try to design and then feed and create animated version of the this phase 3 part color sorting machine. That is one setback or an issue. And I have been trying with my classmates or teammates to be able to finish all these materials. Thank you.